Alright, what's going on, everybody? We are in the home stretch. This is the last notes for this section. There might be some extra example problems that I do. It's such few amount of slides, and I feel like I can actually explain it better not actually doing it in slide form. So what we're going to be caring about now is what if we are on an inclined plane? We did an example problem, and in fact, I literally just did an example problem. I have the papers right here, where we talked about forces being in inclines. We talked about, this was the boat example in my extra example problems where we had to break it into vectors. We talked about a rope being in an angle when you pull something. But what if the object itself is on an inclined plane, not the forces that it's experiencing? So what I mean by that is we'll do an example of this, but I'll show you what I'm talking about here. Let's say that we have a slope, and we're gonna go ahead and draw this slope here. And let's go ahead and just say we'll say it's a ski slope. That'll be convenient there. So we're gonna have our skier. It's gonna be one of the best drawings that I've drawn my entire life. Got a little scarfy scarf coming off of here. He's got his ski poles and we've got his skis. So this skier is going down this slope, and let's think of all of the forces if we were. As I realized I wasn't even on screen. Let's take a look at this slope, and let's try to figure out what are all of the forces at play while this skier is positioned on this slope. And for now, we can just think of it, instead of as a skier, we can think of it as just a box. Let's pretend it's not moving at all. There's no weird accelerations or anything we have to think about. Let's just have a box that's resting on a inclined plane. So if we have our box, well, first of all, there's always gravity. You've realized at this point that every question involves gravity. Your instinct might be to make gravity go this way, but remember, gravity always goes straight down towards the center of the Earth, and the center of the Earth does not tilt just because you go on an inclined plane. So gravity is actually going to be going in this direction. The normal force, if you remember, is always perpendicular to the surface that you're on, which means the normal force is actually going to be pointing this direction. And then if your object is staying stationary on here, that means that there must actually be some friction at play that's preventing it from sliding down the hill this direction. So friction must be helping it stay up and be pointing in this direction. Now, one very important thing to note here, and this is going to be the key to solving these types of problems, is if I have a theta right there, that theta is the same angle that is right here. This is due to some of those angle properties that we talked about, or that you've probably talked about in your math class. Dang it, I just keep moving off screen, man. Sorry, guys. So this angle here, due to the angle identity properties that you've probably learned about in your class, and with the whole perpendicular, parallel lines, etc., etc., this angle of theta here is the same angle that's going to be right here. And the important part is that means you're going to be able to split your gravity into an FG in the, we'll call it the Y direction, but it's not really the Y direction. It's this angle. We try to treat the box as though it's like this, and we just, because gravity is the only one that's tilted if you think of it in this direction, we assume that this is the normal position, and we just make gravity's things vectors. Otherwise, you're going to have to make all of these other things into components, and that's just way more work. So, and then this is the force of gravity in the X direction. So this is why, if there wasn't friction here, as I've voice cracked slightly, your objects would just get pulled down the slope, because gravity is directed downwards, meaning there's a component holding it in place, but there's also a component that's pulling it this direction here. And because the normal force will support it from this direction, that would mean it would just start sliding in that direction. It would start sliding down the slope. So if I were to draw this away from the slope, if I were to draw this tilted and angled vertically, we would have the normal force going upwards. We would have frictional force directed to the left. And then based on this angle here, we would have FG cosine, because it would be the adjacent theta. And then in this direction, we would have FG sine theta. And all of this would be acting on that box, but again, it would be acting tilted. It won't actually be acting up and straight up and down. So that's a little bit weird. It's a little bit hard to grasp. This is probably the trickiest part of the whole chapter to grasp, is being able to solve problems like this involving inclined planes. But let's go back up here and let's think about our skier in my example here. So I'm going to say that this skier, with all of his gear and his equipment, weighs 100 kilograms. We're going to say that the angle here is 30 degrees. And we're going to say that the coefficient of kinetic friction is equal to, we'll say 0.1. It's skis and it's snow. So it should be pretty low. And so this is what we're going to be kind of thinking about in regards to all of our information. So first of all, we know that the total force of gravity, as always, is equal to mass times gravity. So it'll be 100 times negative 9.8. So it'll have 1 to negative 980 newtons. That's the force of gravity. But because of that force of gravity, and because it's not being pulled in one direction this time, we actually have to split it apart. So we'll have the force of gravity in the x direction, which is the actual plane that it's traveling down, which will equal, in this case, it will be, for x direction, yep. Yes, okay. Just making sure I didn't state something incorrectly. 980 times sine 30. And then our force of gravity in the y direction, the direction going downwards here, that's adjacent, so that'll be negative 980 times cosine of 30. So I'm going to go ahead and plug both of those values in really quick in my calculator, because this is how I assume you guys would solve the problem. But I'm going to end up showing you at the end of this there is a little bit of a trick involved that can save you some time with these. So negative 980 sine 30, negative 980 sine 30 is negative 490. Negative 980 cosine 30 is a less pretty number, which is negative 848.704895.7. Now, because we now know the force of gravity in the y direction, because we have this number, we can use that to find the normal force, because the normal force is the force that's counteracting, and it doesn't mention that the skier is sliding off the slope or is flying up the slope. So there must be the sum of the forces in the y direction is 0, which means our F of gravity in the y direction plus our normal force must be 0. So in this case, we know our force of gravity in the y direction is this. That means our normal force must be positive 848.7048957. Sorry for shaking the camera as I write my big number over there. And then finally, because we know the force of friction is equal to mu of kinetic coefficient, the coefficient of kinetic friction, times the normal force, we're going to take this number and we're going to multiply it by our 0.10. We get 84.87. And again, so our normal force would be positive, but this is going to be directed backwards, so it's going to be negative again. So I got 84 point, again, we'll just move the decimal one, 8704895.7. So now we've got force of gravity in the x direction, force of gravity in the y direction, normal force and the force of friction. That is every force that is involved in this problem right here. So we can go ahead and we can figure out its acceleration. We know that our normal force and our gravitational force in the y direction canceled out. So now we're going to, because this is going downwards, this gravity in the x direction, we're going to make that a positive 490. I apologize for that. Because this is to the right is going to be positive. It's all down. It makes these problems. This is part of why these problems are so weird. So sum of the forces in the x direction is also going to be equal to the mass times the acceleration, and it's not going to be equal to 0. It's going to be equal to the force of gravity in the x direction plus the force of friction. Now friction is going to be negative, and our gravity is going to be pulling us down, which in this case is going to be actually angled this way, which means it's going to be in our positive direction. So we're going to go ahead and put equals, and then we're going to say force of gravity in the x direction is right here. We've got our 490, and then plus our negative 84.8704897. And then we're going to divide that by the mass, which we just said our skier has a mass of 100 kilograms. So we'll get an acceleration of 490 minus that number divided by 100 is 4.05 meters per second squared. Now, acceleration of 4.05 meters per second squared for our skier coming down this hill sounds pretty good. But what if I told you that it would be the same acceleration at 100 kilograms as it was at 20 kilograms, or 10,000 kilograms, or 1 kilogram? All of these values would have the same acceleration as they go down this hill. And that may seem like I'm being crazy, but we can actually prove this really quick. So I'm going to pause the video because this is an area where I could very easily screw something up, and I don't want to do that. So I'm gonna pause this really quick and make sure I got it correct. Okay, I believe I have double-checked my work, and I hope that I will explain this without any complications or confusions. If I don't, at the end result, it will all hopefully make out the same way. So let's backtrack from our question was about the x acceleration because x was down. So if we solved for that, we got acceleration is equal to sum of the forces. Actually, let's start with just this. Actually, let's start with the sum of the forces equals mass times acceleration. I think it'll be easier. We're looking for acceleration though. So our sum of our forces in the x direction is equal to the force of gravity in the x direction, which we talked about, plus the force of friction. Okay, well, how did we solve for force of gravity in the x direction? Well, force of gravity in the x direction was mg sine theta. That's the piece of information that we used for that one. And for friction, we used the coefficient of kinetic friction times the normal force. Well, how did we solve for the normal force? Well, the normal force, in this case, because of the situation that we were in, our normal force was equal to the negative, or the inverse, of our FGY. And our FGY was mg cosine theta. So if we were to backtrack, and if we were to actually re-plug in all of these things into this equation here, sum of the forces in the x direction is equal to mg sine theta minus, because of this negative right here, minus mu k mg cosine theta. And we just set up here that sum of these forces is equal to mass times acceleration. And if you notice, if we get to get acceleration by itself, mass is on both of those variables and on the bottom. So we can actually cancel them out, which means to find acceleration down a slope, you do not need mass. You actually don't have to have mass to find the acceleration of an object going down a slope. So the equation you'll use is acceleration is equal to, and this part here is it's a little bit weird, so it's going to be plus or minus depending on up or down in this case. Oh, sorry. Now I'm mixing up my two concepts. Don't even worry about that. We'll get g sine theta, which is this piece right here, minus mu k g cosine theta. This thing, ignoring my weird note that I had on a different piece I was working on, this bad boy right here will help you figure out. All you technically need to know to find acceleration down a slope is what is gravity, which on Earth you pretty much always know, what is the theta of the slope, and what is the coefficient of kinetic friction. And you can find the acceleration that an object will experience as it goes down that slope. All right, everybody. I hope that made sense. If you have any questions, please give me a shout out, give me an email, let me know. If there's anything I can do to help you. I think I might do one extra video where I go over an example of how to solve a problem related to this. But in the meantime, this is Mr. Diamond. If you have any questions, please email me. Hope you have a good rest of your day, everybody. Hope to see or hear from you soon.